Okay, so the next hurdle that we're going to jump in this course is to try and understand the laws of probability. This chapter tends to be challenging for students, and statistically, it's a rough chapter for people. So, I really want to help with that. I'm going to start off by explaining all of the things in these lovely blue boxes in your book and what do they mean. So let's just go through these and make sure we understand. Okay, so for starters, the law of large numbers. I don't know how well you can see that using this iPad, so I'll zoom in a little bit and read it to you. It says, as the numbers of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So, for example, you would say, and I'll just write this over here, what's the probability of getting tails, okay, on a fair coin? Well, you'd say that's a 50% chance, 0.50, right? But think about it like this. Repeat the experiment, say 5 times, right? Maybe, for some odd reason, maybe 4 out of those 5 times, I got tails. Okay, but then 4 out of 5 would be 0.80. All right? But then the law of large numbers says if I, keyword, repeat, as the number of repetitions increases. So now what if I flip my fair coin 100 times? All right, now let's say I actually flip it 100 times. Maybe 48 out of 100 times I got tails. Okay, that's still a 48%. Still not quite 50%, right? So I like to think of this as the theoretical. So really what we're talking about is theoretical versus experimental. And really, as the number of times you repeat that experiment should tend towards the true theoretical probability. They should be equal. Okay, for example, now flip the coin 1,000 times. Maybe 499 times out of 1,000 you got tails. Okay, well then that's 0.499. See, and so 0.499 is getting awfully close to the true 0.5 that we were looking for. Okay, so that's all really the law of large numbers is saying, and I'll erase that there so you can see that. It really has to do with this idea that if we repeat we don't want to run an experiment once or just twice. It would be ideal to run it many, 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 many times. Later on in the course, we'll see how the central limit theorem takes care of that for us so that we don't have to actually physically repeat an experiment 1,000 times. But I'm going to hold that thought. Okay? Let's find the next important. Your author always puts everything in blue boxes or orange boxes. That's important. So let's take a look at the next one. Aha, found another one for you. Okay, rules of probability. Now, I already have podcasts that sort of put all the rules and laws of probability all into one, but I like that we kind of parcel this out a little bit. Rules of probability. So the probability of an event E, and now you'll get exposed to this language here. Probability of event E, and we'll designate that P of E, must be greater than or equal to 0 and less than or equal to 1. So you see here, that means 0 has to be less than or equal to the probability of the event occurring, which is simultaneously less than or equal to 1. All that's saying is that the probabilities that we're about to compute should be somewhere in between 0 and 1, inclusive. So you're not going to get a probability that's 125%. Okay? It'll be 50% or 80% or 20%, something in between 0 and 1. Okay, the next thing is, for number 2, the sum of the probabilities of all the outcomes. I should say more about, before I say that, I should say more about 0. What does 0 mean? It means it's not going to happen, right? So what's the chance that it rains today? If you say 0%, there's no chance that it's going to rain today. If you say 1, okay, there's a 100% chance that it's going to rain today. So just we're interpreting the 0 and 1 there, I should mention. Okay, and then in number 2 here, the sum of the probabilities of all outcomes must equal 1. That is, if the sample space is these various events, then the probability of all these various events added together, total probability must equal 1. Okay? For example, and I'm just sticking simple so you can wrap your head around it, think of a fair die, right? How many faces? 6 faces, right? What's the probability of getting an even number? Okay, 3 out of 6. What's the probability of getting an odd number? Okay, 3 out of 6. But 3 out of 6 plus 3 out of 6 is 1. Okay, so, and if you think about it, even or odd, those are all, that's the all, keyword all outcomes. Those are the only possible outcomes that could happen. You're going to get an even or you're going to get an odd, right? So it makes sense that those two probabilities added together have to equal 1. Okay, let's go to the next magic box. See, I told you anything important would be in a blue or a yellow box. Here's the next thing. The idea of an unusual event. So for your author in particular, they're deeming the word, so be on the lookout for the word unusual. When they ask about unusual, they mean it has a less than 5% chance of occurring. Now, I like what your author does here. I'm going to try and zoom in on this caution note here. It says, caution, a probability of 0.05 should not always be used to separate unusual events from not so unusual events. For example, there's times where, especially if it's a life-death situation, where a 3% chance of occurrence, it's just too high. You want it to be something really, really close to 0, okay? But for the homework questions and things like that, when we say something unusual, we're going to be on the lookout for, less than 5%. And just like I said, that's just with this textbook. You might get another textbook off the shelf and it might say something different. Okay? Let's see the next important box. And by the way, in this podcast, I'm not just going to read things out of boxes. My goal is to get through these boxes and get to the homework problems and do homework with you. That's what you really need help with, someone to sort of guide you through the homework. So that's what I hope to do. But here we go, another lovely box. First, we're going to talk about different approaches to probability. When most people think of probability, they think of the classical approach. But you'll see in some of my other podcasts, probability, you could have the empirical approach, the classical approach, or the subjective approach. The empirical approach to probability is based on events in the past. So with this, I could read this box to you, but basically think about batting averages, something simple like that, or like foul shot average. Okay, so if we're thinking about batting averages, say my batting average is, let's say, 0.256. What does that mean? So that basically means of 1,000 at-bats, see, tenths, hundredths, thousandths, place value. So of 1,000 at-bats, I'll have, and I'm just writing on top of here, I'll have 256 hits. In reality, for me, it would probably be a lot lower. I'm not that good at baseball. But the main idea is that it's based off of past. So, I always think of Shaquille O'Neal or any of those basketball players and their foul shots, right? How in the past, how many foul shots have they made out of 100, out of 1,000, right? So you see here, more formally, it's the frequency of the event divided by the number of trials of the experiment. So how many times that experiment was repeated. And then then you're counting the frequency of the thing that you're interested in looking at, whether that be hits or foul shots or whatever it may be. Okay, so just bear in mind, empirical approach is based on past events, and classical approach is you're counting the number of successes divided by the total number of outcomes. Let's take a look at that, which we'll be doing most of the time for this course. Okay, so here, compute probability using the classical method. You see here, so I'm just going to highlight classical method. You take the number of, probability of V is the number of ways event E can occur divided by the number of possible outcomes. More formally written like that. Okay, well, let's just take an easy example. What's the probability you get a king? Now, note to self, if you've never been out of a standard deck of cards, so every now and then I'll get somebody in the classroom that never played with a standard deck of cards, and so just note to self, standard deck, I'm not talking about a pinochle deck or anything like that, standard deck, 52 cards. I always say maybe just go to the dollar store, CVS, and get a pack if you're not familiar, because a lot of my questions involve cards. But you've got 4 suits, hearts, diamonds, clubs, spades, etc. So, and half the deck is black and half the deck is red. So the probability that you get a king, well, people that are familiar with cards would say 4 out of 52. Because there's 4 kings out of the total number of cards, which is 52. So what you're really doing is you're counting the total number. I like to think of it like this. You're counting the total number of successes divided by the total possible outcomes. And that's how we use the classical approach. It's going to get deeper here in a moment, but like I would say, all right, what's the probability of selecting a heart? Okay, well, that's 13 out of 52. I'll just write this here. Probability of selecting a heart, 13 out of 52. How come? Because there's 13 hearts out of the 52 cards that are in the deck. It's going to get deeper, but let's hold it there for now. Okay, now what I did here, and I hope I can sort of zoom in on this birthday problem, I like to cherry pick these sort of all-encompassing problems from your book that sort of illustrate all these rules that we've been talking about. I'll read it to you first. Birthdays. Exclude leap years from the following calculations and assume each birthday is equally likely. Okay, so for part A here, determine the probability that a randomly selected person has a birthday on the first day of a month and interpret this probability. Okay, well, think about it like this. How many days are in the year? 365. And then think about the first day of the month. Well, there's 12 months, and there's 12 first days of the month, if you will. So we'll be looking at 12 out of 365. So note to self here, for part A, 12 out of 365. So I'll say that again. We're using the classical definition of probability. There's 365 days in a year. There's 12 first days of the month. And so that's how we're getting that. And you can see we're just at the beginning. You can see it's a very thought-provoking chapter because it's abstract. You have to use all these laws, and these laws are going to evolve pretty quickly. Okay, let's try part B. Determine the probability that a randomly selected person would have a birthday on the 31st day of a month. So I always think like this. 30 days past September, April, June, and November. All the rest have 31 except for February. So 30 days past September. So September, April, June, and November. All the rest of 31 except for February. So basically I've excluded 5 months from, or if you need to look at a calendar, look at it. But so then 12 minus those 5 months that I excluded, that'd be 7. Aha! Okay then. So for part B, 7 out of 365. Let's see if I have room here. Yeah, so for part B, we're looking at 7 out of 365. Because only 7 of the months have 31 days in them. All right, let's try again. Part C, determine the probability that a randomly selected person was born in December. Well, that means you could have been born any day in December. So how many days are in December? Hopefully you're thinking 31. That's good. So for part C, if you're thinking 31 out of 365, that's good. All right. Now let's try part D. And just so I have some space here, I didn't want to bring up the blank notebook. I figured I could just write right on here. Part D says, determine the probability that a randomly selected person has a birthday on November 8th. Well, think about it like this. November 8th, that's just a one-shot deal. That's one exact day out of the year. Okay, so that's 1 out of 365 chance. Okay, that's like if I go up to somebody on the street, what's the chance that their birthday is on November 8th? Very slim, right? So your gut tells you there's a very slim chance. Be your lucky day if that happened, right? So 1 out of 365. And it says interpret this probability. Well, if you just grab a calculator and type 1 out of 365, we should look at what you're going to see. 0.0027. That's a 0.2. That's a less than 1% chance. So that's why I said slim chance. All right. Now let's go ahead and try part E. If you just met somebody and she asked you to guess her birthday, are you likely to be correct? So that's kind of the same thing as saying, that's basically asking you, what's the chance that you're going to guess that person's birthday correct? Very slim, right? 1 out of 365, that's not likely. And then part F says, do you think, now later, I wanted to throw this in here, later we're going to compute the probability that if you have a room filled with 30 people, what's the chance that 2 or more have the same birthday, that at least 2 people have the same birthday. That one goes against your gut instinct. You would think that that would not be very likely, but it actually is. So, considering. But let's hold off that question till later. Now let's talk about part F. And part F, if I can zoom in here, it says, do you think it's appropriate to use methods of classical probability to compute the probability that a person is born in December? And yes, that's exactly what we did. We said, look, December, there's 31 days, so that's the total number of successes, 31, out of 365 total days in the year. So we did use the classical definition of probability to do that. We counted the number of successes divided by the total number of outcomes. Okay, hope that helps. That was just our introductory section. Okay? Okay, now I did have, that was our introductory section, but I did have just one last problem, I promise, that from the homework that I wanted to work through with you. Like I said, it's always good practice to run this through with someone. Let's try 54. Right here. Okay. It's called Putting It Together, Drug Side Effects. In placebo-controlled clinical trials for the drug Viagra, 734 subjects received Viagra and 725 subjects received a placebo. Subjects did not know which treatment they received. Later we'll talk about the design of experiments, the placebo effect, all of that, but not now. The table in the next column summarizes reports of various side effects that were reported. Okay, so now this much, in other words, for now, I just want to practice reading tables and interpreting tables. Okay, so here's the table, and I hope you can see it okay. We have these various adverse effects, like side effects, headache, flushing, nasal congestion, diarrhea, etc. We have the number of people in our Viagra group that received that drug and how many of them experienced certain side effects. And then we have the placebo group here, and how many of them experience certain side effects. And this is just one of those, it's called a putting it all together problem because it makes you understand the language that we've used thus far in the course. So, for example, in Part A, it says, is the variable adverse effect qualitative or quantitative? Okay, and you would say it's qualitative because if I ask you what kind of adverse effect did you have headache, did you have nasal congestion? Those responses, these responses right here are, note to self, qualitative, okay? Which type of graph would be appropriate to display the information in the table? And I like this question because at the beginning of the term we said if you have qualitative data, you can display it with a bar graph or a pie chart. Okay, and then it says to construct the graph. I'm not going to do that right now. I just wanted to, we've done that in the past. Just wanted to reiterate that a bar chart would be appropriate here. Okay. Part C, what is the estimated probability, that's what I want to get into, probability, that a randomly selected subject from the Viagra group reported experiencing flushing, and would this be unusual? Aha. Now let's zoom in here. How many from the Viagra group experienced flushing? 73. And how many total were there? Aha. 7. So now we're using that classical definition of probability, is what we observed. So for part C, we're looking at 73 out of 734. And then a lot of people say, well, should I turn that into a decimal? Well, let's do that just to see how likely it is. 0.099, because it says, would it be unusual? And remember, to your author, that means less than 5%. So, with this, you're looking at 0.099, so it's definitely not less than 5%. So would this be unusual? We're going to say no. Okay. Then in part D, it says, what's the estimated probability that a subject receiving a placebo would report experiencing flushing? Okay, I'm going to do that with you. Okay, so now let's look at the flushing for the placebo group. Aha, 7 out of 725. Okay, so for part D, we're looking at 7 out of 725. Well, and it says, is that unusual? Well, let's look at the decimal. 0.0096. So rounded is about 0.0097 if you're rounding. Okay, well that is definitely less than 5%, right? So would this be unusual? Yes. All right. And then in part E, it says, if a subject reports flushing after receiving a treatment, what might you conclude? And you might logically conclude that they came from the Viagra group, right? You'd be surprised if they came from the placebo group. Something like that. Okay? So I hope that helps. I'm actually going to stop the podcast here for our introductory section, but in the next podcast I'm going to start to talk about the rules of probability, like unions, complement rule, the ands, the ors, okay? We're going to get into all that on the next one. All right, good luck, everyone.